Okay, so part two. What we were doing in the last couple of problems, we were finding the slope of tangent lines at specific points. So we had to go through some manipulation in order to get there. But what if we want the slope of tangents to a function at multiple points? Like at 3, 5, negative 1, 4, and 0, 2. Now you have two options. You can either go through what we just did multiple times, so 3 times, to get the answers, or you could do what we're about to do next. You can find a little formula that you can just plug these into and find the slopes that way. It still takes some work, but it's going to save you some time in the long run. And it's the whole idea of derivatives that we're about to get into here in a second. Okay? So, what if we want to find the slopes of tangents to this function at several points? And we need to use the generic formula to begin with, meaning I don't want to call it c in the beginning, I just want to use a generic x. And here's what I mean by that. I want to use that difference quotient. The limit, as delta x approaches 0, f of, I'm going to put x plus delta x, because c stands for a specific number, like a 1 or 2. I just want to call it a generic x value for right now. Minus f of x over delta x. So this probably looks a little familiar. Again, it's a difference quotient, but we're not going to plug a number in for x. We're just going to generically use this function right here and not plug any numbers in. Okay? So this one gets a little messy, so bear with me here. The algebra gets messy. So we want to plug x plus delta x, that's our input, in for this x here and this x here. Okay? So when I find f of x plus delta x, I'm going to plug this in for both x's. So I'm going to have x plus delta x squared minus 2 times x plus delta x plus 2. That plus 2 comes from right there. So this is f of x plus delta x, and we'll have to actually do all this work here in a second, not yet. Then it says minus f of x. So now we're going to subtract the original function. So minus, and then in parentheses, x squared minus 2x plus 2. So we're subtracting the original function right here, all right? All over delta x. Okay, well, let's do some algebra, all right, to clean this up. So limit, as delta x approaches 0, we want to square this quantity. So again, I'm going to use that shortcut. Square the first, take the product and double it. So the product would be x delta x, double it. So 2x delta x. And then square delta x. Distribute negative 2. So minus 2x minus 2 delta x plus 2. And then distribute the negative in here. So minus x squared plus 2x minus 2. All over delta x. Are we having fun yet? What's nice at this step is that things cancel out. Okay, what's going to be happening here is we're always going to eventually be able to cancel out this delta x. Let's see what happens. X squared minus x squared, those cancel. Let's see. Negative 2x plus 2x, those cancel. Positive 2 and negative 2, those cancel. And so you notice every term left in the numerator has a delta x in it, which is extremely nice because then we're going to be able to cancel this out on bottom. So we're going to factor a delta x out of the numerator, so limit, as delta x approaches 0. Let's factor a delta x out, so we have 2x plus delta x minus 2. Over delta x. The delta x's cancel. And now when we plug 0 in, look what happens. In the other problems, when we plugged the 0 in, we would get a numeric value because we were looking for the slope of the tangent line at a point. What we're doing now, look at what happens when we plug 0 in. When I plug 0 in for delta x, we get 2x minus 2. What this does, this will find the slope of any tangent line at any x value we want for this specific function. Basically, this stands for slope. This little thing we found here stands for slope. And so now what we can do, if I want to find the slope of the tangent line of this function at 3 different points, well, look at what we can do. If I want to find the slope of the tangent line at 3, 5, I just plug the x-coordinate in for that slope function we just found. So 2 times 3 minus 2 is 4. That means the slope of the tangent line of this given function at 3, 5 is 4. If I want to do negative 1, 4, plug negative 1 in for x. 2 times negative 1 minus 2, that's negative 4. So the slope of the tangent line of the function at negative 1, 4 is negative 4. And then we can do the last one. So 2 times 0 minus 2 is negative 2. So the slope of the tangent line of the function at 0, 2 is negative 2. So this is a generic way to find a slope, a little expression for slope that if you want to evaluate at multiple points. So you have a couple options here. You can either use the original one with the c and plug the number in immediately, or get the expression, which this is called the derivative, which we're going to talk about here in a second, and use it to find slopes at multiple points. So this process we just talked about with these generic x values here and not the c values, this process is called differentiation. It's called differentiation. Differentiation. What it's doing, this process, is finding the derivative of this function. It's finding the derivative. The derivative is what allows you to find slopes of tangent lines at specific points. So this right here, this 2x minus 2 we just found, is the derivative of this function. A derivative finds slope for you, slopes of tangent lines at specific values. So this is finding the derivative. And there's some notation that you might see, and so I just want to write this notation. You can denote a derivative. A lot of times you'll see it as f prime, so f apostrophe. So this stands for the derivative of f. So when you see that apostrophe, this is the derivative. If it's a y, you might also see it as y prime. And another notation you could see is the derivative of y in terms of x is what this means. You'll see dy over dx. And this is common notation as well, but this stands for the derivative of y in terms of x. These are all nouns. These stand for what the derivative is. So for that last problem, we could have said, when we found the 2x minus 2, we could have said f prime of x equals 2x minus 2. Basically, the derivative of the function is 2x minus 2. A command you might see, if you see dx of f of x, this is a command right here. This is telling you to find the derivative of the function. So this is a command, it's like a verb. Or you could see another notation like this. This is a little more uncommon. I don't know how often we'll see it come across this. This is what's typically used, the notation that you'll see. But these are verbs. These are doing something. These are like telling you to find the derivative. Okay? But just some notation. So the definition of derivative, because I know you guys know some shortcuts in physics, but the definition of derivative, which you are required to know, is this. If you want to find the derivative of a function, meaning the expression that will find slopes of tangent lines, you take the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. This is an important definition, and this finds you the derivative of a function, which allows you to find slopes of tangent lines at specific points. Okay? Alright, so it's the definition we're going to have to know and understand what it's doing. It's basically finding slope between 2 points as the x value between those 2 points gets really close to 0. And that's what this is doing. Okay. So example 3 says, find g prime of x at 1, 3, and 3, negative 5 if g of x equals 4 minus x squared. Anytime it says find g prime of x, they're asking for the slope. All right, g prime, anytime you see derivative, think slope. All right, so we want the slope of the tangent line. That's what g prime of x is, derivative. at these 2 points. So what we want to find is the derivative of this function. We want to find the derivative of g. All right, so we have to go through that process we just did in that last problem. So g prime of x is going to be the limit as delta x approaches 0 of g of x plus delta x minus g of x over delta x. So we're going to use this function, use our derivative definition right here, and find the derivative of this function. So let's apply it. We're going to have the limit as delta x approaches 0. We're going to plug x plus delta x in for the function right here. Again, this is our input. X plus delta x, plug in for x here. So we're going to have 4 minus parentheses x plus delta x squared minus g of x, so minus the function itself, minus parentheses 4 minus x squared. If you just want to flip the signs there and not put the parentheses right away, that's fine. But I'm going to put in parentheses to show what we're doing. And we have to do some algebra to clean this up. And we have to square quantities, distribute, combine like terms, all that good stuff. So we're going to have limit delta x approaches 0. We have 4 minus, and now when you're squaring this, keep it in parentheses, because this minus is going to be going to everything we do when we square here. So parentheses, square the first, double the product, so 2x delta x, square the second, delta x squared, and then distribute the negative. So minus 4 plus delta x squared. Or matter minus 4 plus x squared, not delta x squared, over delta x. All right. So now I'm going to have the limit as delta x approaches 0. I'm going to distribute the negative, so I'm going to have 4 minus x squared minus 2x delta x minus delta x squared minus 4 plus x squared over delta x. And this is the step that's nice, because this is when things cancel. So the x squareds cancel, the 4's cancel, 4 minus 4. And now you have delta x in each term in the numerator, so pull delta x out. So you have limit as delta x approaches 0. Factor a delta x out. So you have negative 2x minus delta x over delta x. Now they cancel. Now you plug 0 in for delta x, and then all you're left with is negative 2x. What we just found is the derivative of 4 minus x squared. This is the derivative of 4 minus x squared. And this will allow us to find slopes of tangent lines at any specific point along this graph that we want. So our 2 questions said, find the derivative at 1, 3, and 3, negative 5. We want to find the slope at 1, 3, and the slope at 3, negative 5. So, at the slope at 1, 3, we're going to plug the, remember the x value in for x, so negative 2 times 1. So negative 2. That's the slope of the function at 1, 3. And then the slope at 3, negative 5. Plug in 3. Negative 6. Then it says, what are the equations of the tangent line? So we've been talking about slope this whole time. But now we want to know, what are the equations of the tangent lines at these points? Well, think about what you need to find the equation of a line. Okay? And I talked about this in one of our first review games. To write the equation of a line, you need to know the slope of that line and a point from that line. Because if you know the slope of the tangent line and a point from the line, you can use point-slope form. And we're going to use point-slope form. It's y minus y1 equals m x minus x1. So we want to find the slope of the tangent line first at 1, 3. Okay, well, we know the point is 1, 3. We know the slope was negative 2. So we have all our information. So for the point 1, 3, the equation of the tangent line would be y minus the y-coordinate, 3, equals the slope that we found, so -2, and then x minus the x-coordinate, so x minus 1. And you can leave that answer. You don't have to distribute the -2. You don't have to put it in slope-intercept form. Leave that. That's it. That's the equation of the tangent line at 1, 3 for that function. At 3, -5, same thing. Y minus the y-coordinate, so y minus -5 is y plus 5. The slope at that point was -6, and then x minus 3. And again, you don't have to put that in slope-intercept form or anything like that. You can just leave that, and those are the equations of the tangent lines at those 2 points. All right, I'm going to stop and create a third video just so it doesn't mess up on me. So I'm going to stop this now and do the last few.